Hello everyone, today I'm going to talk about a type of helicopter configuration that seems crazy, arbitrary and doable, but why at first, but when you get a little bit deeper into it, turns out to be logically well reasoned and really clever, at least for certain purposes. But first of all, I'm always open for any questions or suggestions. If you have any questions about aerospace engineering or tangent topics like aerospace history, although I prefer engineering because it usually goes with logical reasoning and understanding rather than just trivia. I am trying to increase the frequency and quality of these explanation videos. I do have a few projects right now, so I'm a little bit short on time, but I'll always try to get around to it, and a video about the futuristic possibility of antimatter as a rocket fuel is also planned, but for now we'll focus on the way more earthly topic of helicopter designs with the Flettner twin rotor, which is a type of intermeshing rotor system, which sounds crazy at a first glance if you're not that familiar with helicopter technology, because, well, you've got two rotors, two very fast spinning, dangerous objects that are hard to control, intermeshing with each other, synchronized, and they may never hit each other, but really that's relatively easy because they are mechanically locked. The gears that drive these rotors are connected to each other. They are driven by the same engine, which might still be several engines which are bundled together, but they are driving both rotors. These two rotors are mechanically locked, and there is absolutely no way that one rotor would ever spin at a different RPM than the other rotor, so they can't hit each other. They are locked in a 90-degree offset position and keep intermeshing without ever hitting. And yet the separate control of these two rotors can be used as an axis, which is of course because helicopters don't actually use rotor RPM to control anything. They try to keep rotor RPM stable and use pitch to control everything, including the amount of lift. If a helicopter wants to go upwards, it doesn't spin its rotor faster, it increases its collective pitch, it increases the angle at which the rotor blades are hitting the air, essentially just like an airplane that goes up, pitches up, thus increases the angle at which the wings hit the air, and thus creates a higher speed of airflow and more lift, which not only increases the amount of torque that this rotor produces, but also increases the ratio of torque to lift because, well, the angle of the rotor blades has changed, the angle of attack has increased, and the rest is trigonometry. You get more induced drag on the rotor blades, if you see them as wings, and therefore more torque per lift ratio. For this explanation of the concept, it's slightly simplified, but you might say that the torque is actually proportional to the square of the angular attack or the pitch, because more pitch means more lift, but it also trigonometrically means that each lift contributes more to induced drag, while the lift itself is roughly proportional to the angle of attack. And this is going to become important later. Now, the most visible feature of these Flettner rotors is that they are angled against each other, so each is slightly tilted, usually to the left and right, and the axes of these rotors actually intersect at the center of the cabin if you extend them. So you've got a huge advantage, which is a little bit complicated to explain, but you've got two rotors, but they are not coaxial rotors, so they're not. You don't have a lower or upper rotor, and the aircraft is basically symmetrical, which coaxial rotors are not, because the upper rotor spins in one direction and the lower rotor in the opposite direction, and which one is which. And at the same time, unlike usual twin rotors or tandem rotors, you still have the rotor axis intersect, which happens ideally at or very close to the center of mass of the whole helicopter. And what this means is that you can increase lift on one rotor while decreasing the lift on the other rotor without creating any pitch or roll torque. If you imagine a tandem helicopter or twin rotor helicopter changing the amount of lift produced by each rotor so that they produce different amounts of lift, you would create some roll or pitch torque because, well, one rotor would go up and the other one would go down. In this case, they're intersecting at the center of mass, so there's no torque actually created by the lift force. And what that means is that you can control your yaw movements really easily, much easier than with any other helicopter concept. You increase pitch in one rotor, decrease it in the other, the overall lift stays the same, one rotor creates more torque than the other, and the helicopter spins in the opposite direction of that rotor. Obviously, the two rotors spinning in opposite directions, if they have the same amount of pitch, cancel each other out, so you don't need an anti-torque system like a tail rotor. And you can also control your yaw movements by controlling the separate pitch of both rotors. This is also done by coaxial or, to some extent, twin and tandem rotors, though they are a little bit more complicated, but mostly coaxial rotor helicopters. But it's a lot more complicated there because the lower rotor is exposed to the downwash of the upper rotor, which is spinning along with the upper rotor, so the lower rotor essentially has a higher RPM, but by a different amount depending on the pitch of the upper rotor, and it gets a lot more complicated than it seems at first. I mean, helicopter aerodynamics are always rather complicated, but just the concept itself is already a lot more complicated than it seems at first, so that's a little bit of a problem, especially for old-timey helicopters that didn't have numerical computation tools to design. And of course, in a tandem or twin rotor helicopter, you have the problem that if you use this method for yaw steering, you'll need to counteract the roll or pitch steering because the rotors are at completely separated parallel axes, so they create a torque from their lift. Now you can use additional methods for yaw control in a Flettner rotor, like applying cyclical pitch to nod the helicopter up or down differently on the two rotors, and because of gyroscopic effects, this would happen on a rotor blade that is going into the rising position, not that is right now in the rising position, and thus you would create different amounts of induced drag and thus turn the helicopter, which is relatively complicated and also not incredibly effective. So while it's often being mixed into the yaw control, it's not the main method of yaw control for Flettner rotors. And control along the other axis is just basic helicopter swash plate technology. You use cyclical pitch to nod forward and backwards, to roll left and right, and collective pitch on both rotors to rise and sink. And the rest is of course flying forward by nodding forward, and so on. So the obvious advantages are that you have a relatively simple control system, a relatively simple helicopter design, so it is relatively popular with rather old helicopter designs. You also get a lot of lift area, like with any multi-rotor helicopter instead of a tail-rotor helicopter, so it is really good at lifting heavy loads. However, the rotors do both attach at the center of mass, so unlike a tandem helicopter, it's not that great an idea for a really long cabin. So usually they're not used for heavy internal transport like cargo or troop transport helicopters, but they're usually used as sky cranes with a hook at the bottom that carry any sort of payload below themselves without too much structural load on the cabin. From an aerodynamic and control perspective, they're also somewhat maneuverable, but they do have the problem that blade elasticity is a big problem here because they are intermeshing, so you run a certain risk of them hitting each other if the blades end up being somewhat elastic, and so any bending force on the rotor blades is much more limited than with other helicopter designs. So they're not really well maneuverable at high speeds or with heavy loads, and they're generally not very fast compared to conventional helicopter designs, just like tandem rotors, who also somewhat suffer from unequal loading and from the general helicopter speed limit more than conventional helicopters. They are really good at lifting heavy loads because they have a lot of rotor area, but they're not good at flying fast. Another problem is that you need precise and reliable gears, so that's a bit of a manufacturing issue, and they have a big practicality issue that these rotors, which are slightly tilted to the side, get pretty close to the ground on those sides, unless you build the helicopter to be incredibly high and have a very small rotor diameter. These rotors are going to get close to the ground with their blade tips, which makes landing one safely a little bit more tricky, because if you make a little mistake, that can be a lot more dangerous than with a conventional helicopter, and it's also a lot more dangerous in uneven terrain or with people landing around while the helicopter is in operation, justifying the among fans somewhat iconic warning, approach from front signs, which are usually painted visibly all over the helicopter, because you're supposed to approach and enter that helicopter from the front if the helicopter is operating and the rotors are spinning and you're about to enter on board that helicopter. You're supposed to approach the helicopter from the front, so you don't run any risk of interfering with the rotors, while if you decided to approach the helicopter from the side and you're a little bit taller, you might just end up running into the blade tip of that rotor. Historically, the concept is very old, dating back all the way to World War II and the early 40s, when a German engineer named Flettner came up with the concept, whom it is also named after, and his company started building some experimental helicopters based on this, but back then helicopters were generally mostly about trying to find out if you could get a helicopter to fly rather than about actual operation, and they were never really used for anything. Then, after the war, they started to be used as heavy lifting helicopters, and the most recent well-known helicopter of the Flettner design is the K-1200 K-Max, built by the US company Cayman Aerospace, which was designed in the 90s and produced all the way to 2003 and is still in operation today. And surprisingly, while being the youngest of such helicopters, also happens to be the most well-known and somewhat iconic of them. The shape of its very, very narrow cabin is somewhat considered to be a standard for these rotor designs, although it is a relatively young addition to the concept. This narrow fuselage gets thinner at the bottom while being relatively thick at the top, thus following the airflow of the tilted rotors and directing it to merge at the bottom and most efficiently use the amount of airflow and kinetic energy put into it. The K-1200 is still in operation today for both civil and military use, and one has even been modified into an autonomous drone using much more modern technology, of course. Yet you still see the optimal purpose of this design, as this helicopter is mostly built and used for carrying heavy objects on the outside of the cabin using a hook at the bottom of the helicopter. So this was my little talk about Flettner rotor configurations. I hope you found this somewhat interesting, and as always, thanks for watching.